So we're going to talk about more about polynomials. We're going to do complex numbers, and then we're going to talk about the fundamental theorem of algebra, which has to do with polynomials and their zeros. Okay, so our goal is to be able to write any polynomial in completely factored form, where I use all linear factors. And these are my zeros, so I'll call these C1, C2, C3. Okay, so I want to be able to write it as x minus 1 0 times x minus another 0 times x minus another 0, so that I can completely factor it. And we did some of this last class. We did some problems where we wrote in completely factored form last class. But we didn't see every kind of polynomial. We just did some special ones that we were able to figure out. So let's say we want to do it for p of x equals x squared plus 1. I want to write it in completely factored form. So I need its zeros in order to be able to write it in completely factored form. So p of x, this is sort of the completely factored form. Right, because it's a second degree polynomial, there should be two factors, so that when I multiply them together, I'm going to get an x squared. And the a in front is the same as the leading coefficient on the p of x. So what's that going to be? 1. Okay, so I just need to know what the two zeros are, plug them in for C1 and C2, and I'll be done. So how do you find the zeros of a polynomial? To find zeros, close, you set something to 0. Y, yep. You set the whole polynomial equal to 0. X squared plus 1 equals 0, and you solve. That's how we find zeros. You set the polynomial equal to 0 and solve. So to solve this thing, I would do, well, x squared equals -1, and then square root, uh-oh. What's the square root of -1? I, yeah. So up until right in this moment, we have denied the existence of the square root of -1. We've said, oh, you can't do it, no solutions. We can't get away with that anymore. The square root of -1 we're going to define as the number I. Okay. And this is kind of like when you're growing up learning math. The first numbers you learn about are just the counting numbers, 1, 2, 3, 4, right? And then they tell you that there's actually something called 0, which is nothing, right? And then they teach you about negative numbers, and then they teach you about fractions. And so each year you go along in school, you learn like that your universe of numbers is not the only universe, that it's actually bigger. So we're going to make it bigger again today. We're going to say there are more numbers than the numbers you know about, and they're called imaginary numbers. That's why we call it I. And if it's hard for you to accept, it was really hard for the inventor of every new set of numbers to get people to accept it, right? Irrational numbers, numbers that can't be written as a fraction, a over b. The person who proved that that exists was killed, right? Because he was, yeah, he was a follower of the Pythagoras, and the Pythagoreans believed math was more like a religion to them than sort of an academic pursuit, and they thought that math was intrinsically connected to the earth and the way everything grows and God and stuff like that. And so obviously they're very famous for this theorem, right? A squared plus b squared equals c squared. And one of Pythagoras's followers said, well, if I do this, if I make a right triangle where the two legs are length 1, 1 squared plus 1 squared is 2, which means that the third side has to be square root 2. And he proved, he said, well, square root 2 cannot be written as a fraction. You can't write it as a fraction, whole number over a whole number. And when he showed his proof of this to Pythagoras, he drowned him. Yeah. It just went so against everything that they believed. They believed that rational numbers could explain everything. Irrational, yeah, right. So if it's hard for you to come to terms with the fact that there are more numbers, yeah, don't kill me, please. It's natural to feel resistance to it. Just try to let yourself get past it. Okay, so we have the square root of a negative number. We use the letter I to symbol the square, to denote the square root of -1. So if k is a positive number and I want to take the square root of -k, that's like taking the square root of -1 times the square root of positive k, which is I times the square root of k. So when you want to take the square root of a negative number, just take the square root of the positive number and pull an I out front. For example, the square root of -49, we could write that as the square root of -1 times the square root of positive 49. What's the square root of -1? I. What's the square root of 49? So this is 7I. The square root of -8. Well, let's see. I could rewrite this as the square root of -1 times the square root of 4 times the square root of 2. I just broke 8 down into 4 times 2. What's the square root of -1? I. Square root of 4 is 2. And the square root of 2 is just the square root of 2. So this says 2 square roots of 2 times I. Yes, the I is on the outside. Sure, yeah. Order doesn't matter. It's all multiplication, so I could write it as like that if I want. Yep. Okay, I squared. What do you think I squared is? Close. Well, I squared is I times I, right? And that's the square root of -1 times the square root of -1 -1. Yeah. If I do the square root of -1 squared, the square and the square root cancel, right? And you get -1. I know there's a good argument to be made for 1 also, because in our regular arithmetic, you can multiply stuff under square roots together and then square root it. So if I multiplied -1 times -1, I'd get 1, and then square root it, I'd get 1. But the reason I squared is -1 is because of the way we came up with I being -1 from this equation. X squared plus 1 is 0. I solved this thing and I said the solution is I. So that means that if I plug the I back into this equation, that this is the number that makes this equation true. I squared plus 1 has to be 0. Okay, so you know how usually we do a little check, right? I would say, okay, well, I squared plus 1 has to be 0, which means that I squared has to be -1. It has to do with the way we came up with I is the square root of -1. All right, so this introduces us to the complex number system. Complex numbers are numbers of the form a plus bi, where a and b are real numbers, the kinds of numbers we've worked with so far. So the a, the part with no I on it, is called the real part, and the 5, the number that has the I with it, is called the imaginary part. So some examples: 3 minus 4i, 5 plus 0i, 0 minus 7i. Those are all complex numbers. So is the number 3 a complex number? Yes. Write it in the form a plus bi. How do I write 3 as a plus bi? Something plus something I. You got it. 3 plus 0i. So the regular old number 3 is complex. Now, I want you to, everybody, just black out this whole line. Don't read this. So we can do arithmetic on complex numbers. It's very similar to arithmetic on regular numbers or doing algebra with variables. So I'm going to skip this first one. We don't need it. If I go to B here, I have 2 plus 3i, one complex number, plus another complex number, 1 plus 5i. Now, if I were a variable, what would the answer to this be? How would you add these together? 3 plus 8i. That's how you do it. Nothing new here. You add the real parts, and then you add the imaginary parts. Same thing for subtraction. All we have to do is remember to distribute the negative sign, just like we would if these were x's instead of i's. So it would be 2 plus 3i minus 1 minus 5i. Distribute the negative sign. And then combine like terms, right? I combine my real parts. 2 minus 1 is 1, and 3i minus 5i is minus 2i. What's the matter? I distributed this negative sign to both terms in the parentheses. So this is like a -1 in front that I'm distributing. When I want to multiply two complex numbers, I can just treat them like binomials. I just FOIL. So I do first, outer, inner, last, distribute. So I have 2 times 1 is 2. 2 times 5i is 10i. 3i times 1 is 3i. And 3i times 5i is 15i squared. So I could combine like terms. 2 plus 13i plus 15i squared. But what does I squared equal? -1. Yep. From back, way back here, we said I squared is -1. Okay. So I'm going to replace in that expression, replace the I squared with a -1. So this is going to be 2 plus 13i plus 15 times -1, which is 2 plus 13i minus 15. And then combine like terms, 2 minus 15 is -13. So -13 plus 13i. Okay, you guys try part E. Do this multiplication in your groups. All right, so we FOIL it out. We get 2 times 2 is 4, minus 6i plus 6i minus 9i squared. Minus 6i and plus 6i cancel. So I have 4 minus 9i squared. but I squared is negative 1. So this is 4 minus 9 times negative 1, which is 4 plus 9, which is 13. So something special happened in that example. I did 2 plus 3i times 2 minus 3i, both complex numbers that have imaginary parts, and I got a real number, a plain old 13, right? No imaginary part. So that happened because 2 plus 3i and 2 minus 3i are what we call conjugates of each other. So the conjugate of any complex number, a plus bi, is a minus bi. And reverse is also true. The conjugate of a minus bi is a plus bi. So the conjugate of 2 plus 3i is 2 minus 3i. And we put a bar over a complex number to instead of writing the conjugate of 2 plus 3i, we just write this. That means the conjugate of 2 plus 3i, which would be 2 minus 3i. So it's going to be handy for us to have a shortcut for multiplying two conjugates together, though it's not like it took us much time to do this multiplication problem. Minute maybe. But we're going to do it pretty frequently, multiply two conjugates together. So let's see what happens if I multiply a plus bi times a minus bi for any a and b. When I FOIL, I'm going to get a squared first, right? And then the outer would be minus abi, and the inner would be plus abi. And then the last would be minus b squared, I squared. So the outer and inner terms, negative abi and positive abi, cancel. And then I can replace the I squared with a negative 1, a squared minus b squared times negative 1. So what would my final formula be? The last step here. A squared plus b squared. So it's just a little shortcut. You can use it or not, because you can always just multiply the two together. You don't have to memorize it, but it can come in handy to have the formula. So if I went to go back and do the 2 plus 3i times 2 minus 3i that we did before, and we know the answer is supposed to be 13, right? In this case, a is 2 and b is 3. So this is going to be 2 squared plus 3 squared, which is 13, just what we got when we multiplied it out. Okay, so conjugates are particularly helpful when you're dividing expressions that have complex numbers. So if I want to do 2 plus 5i divided by 2 plus I, the trick is I don't want to have a denominator. I kind of wish that it wasn't there. But it's not an equation, so I can't just multiply both sides of the equation by the denominator and make it go away. So I'm going to use the conjugate to at least transform that denominator into a real number. So if I multiply the top and bottom of this fraction by 2 minus I, the denominator is going to end up as 4 plus 1, a squared plus b squared, which is 5. Just using the shortcut that we just developed. And in my numerator, I'm going to have to multiply out. I'm going to have to FOIL it. So I'm going to get 2 times 2, which is 4. The outer is negative 2i, and the inner is 10i. And then the outer is minus 5i squared. then I just do a little simplifying. So I'm going to have 4 plus 8i. And then I squared is -1. So this is really plus 5. Combine like terms in the numerator, and I have 9 plus 8i over 5. And the goal is to write this as a plus bi. I want it to look like every other complex number. Right? So I am going to divide the 5 into both of my two terms. So this is going to be 9/5 plus 8/5 I. So the trick when you're dividing two complex numbers is multiply the top and bottom by the conjugate of the denominator. Okay, so now that we've had a little super short lesson on complex numbers, we're going to talk about the fundamental theorem of algebra, which says that any polynomial can be written in completely factored form, where all my factors are linear, x minus a 0 times x minus a 0 times x minus a 0. So for a degree n polynomial, there will be n factors, provided we count each 0 according to its multiplicity. So last class we learned that if 3 is a 0 2 times, we say it's a 0 with multiplicity 2. So if you count 3 twice, then we can write it with n linear factors. So for example, x minus 2 cubed times x plus 2 squared times x plus 5 to the 4th is a 9th degree polynomial. It has 9 zeros, 3 of which are distinct, right? So it's got a 0 at 2, because when I set x minus 2 equal to 0, I get 2. And that is going to happen 3 times, because I have 3 factors of x minus 2. So 2 is a 0 of multiplicity 3. -2 is a 0 of multiplicity 2, because x plus 2 equals 0 gives me x equals -2. And that is a factor twice, so it has multiplicity 2. And then x plus 5 to the 4th, that's x plus 5 times x plus 5 times x plus 5 times x plus 5. I set each of those factors equal to 0, and I get x equals -5 4 times. So we say -5 is a 0 of multiplicity 4. So when I write p of x out in completely factored form, I do have 9 linear factors because it has 9 zeros. So it's a little weird to say it has 9 zeros because it seems like, well, it's got 2, -2, and -5. Those are 3 distinct zeros, but some of them happen more than once. So we say it has 9 zeros. So how many zeros or factors, because they'll always have the same number of zeros as it does factors, does this polynomial have? No. Let's go back and reread the theorem. It says that any polynomial of degree n will have n linear factors and n complex zeros. So what's the degree of this polynomial? 3. The highest power of x is a 3, so it should have 3 zeros and 3 linear factors. Okay, so let's find them. I want to find the zeros, and if I have the zeros, I'll have the factors. So the way we find zeros, what we always do to start is set the polynomial equal to 0 and try to solve it. So there's an x in every term here, so I could factor an x out. So I have x squared minus 4x plus 5. Does x squared minus 4x plus 5 factor? To what? -5 and +1. That won't, yeah, that's going to give me a -5 when I FOIL it out. I don't think it does. So what I've got is two things multiplied together, x and this quadratic, and the answer is 0. So either x has to be 0 or x squared minus 4x plus 5 has to be 0. So that's 1, 0. One of my zeros is 0. And to solve this one, since factoring seems to be eluding us, what do? Quadratic formula. Okay, so I get x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a. So that's 4 plus or minus the square root of 16 minus 20 is -4 all over 2. Now what is the square root of -4? 2i. Great. So this is 4 plus or minus 2i over 2. You can divide the 2 into both terms of this numerator. So this would simplify to 2 plus or minus I. So I found 3 zeros. 1, 2, 3. So that's all there are. There's 3 zeros. And now that I know the zeros, I can write down the factorization. I can completely factor it. So see, my polynomial is x cubed minus 4x squared plus 5x. So I now know that I can write it as a product of 3 linear factors, and it's always x minus your 0, right? 0 is one of my zeros. 2 plus I is one of my zeros, and 2 minus I is one of my zeros. So anytime you factor something, you can check to see if you're right by multiplying it back together. So let's see what happens if I do that. So x minus 0, I'm just going to write as x, because why bother writing minus 0? Times x. And I'm subtracting this entire complex number, 2 plus I, which is why I put parentheses around it. So I'm going to distribute the negative. So I get minus 2 minus I. And same thing here. I was subtracting this entire complex number, which is why I put parentheses around it. So I'm going to distribute that negative also, and I get minus 2 plus I. Now, anybody know how to multiply two trinomials together when there's 3 terms? Is there sort of a equivalent to FOIL? Nobody knows? You just distribute. So you just take every term in the first set of parentheses and multiply it by every term in the second set of parentheses. So I'm going to keep the x outside for now. And I'm going to figure out what these two things multiply together to be. So I'm going to start with the x, and you multiply the x by every term in the second set. Okay. So x times x is x squared. X times -2 is -2x. And x times I is ix. Then you move on to the -2. Then you take the -2 from the first set of parentheses and multiply it by everything in the second set. So -2 times x is -2x. And -2 times -2 is +4. And -2 times I is -2i. Then, lastly, you take the negative I. The last thing in the first parentheses, multiply it by everything in the second set. Yep. Can you do what? Oh, next time I print it, you ran out of room? Oh, sure. Do you need some? I have scrap paper. Yeah. Okay, so negative I times x is minus ix. And then negative I times negative 2 is plus 2i. And then negative I times I is minus I squared. All right, so now I'm just going to try to simplify what's in that square brackets there. So a lot of stuff is going to nicely cancel. I have a plus ix. Oops. I have a positive ix and a negative ix, so those go away. I have a minus 2i and a plus 2i, so those go away. And then I can combine some like terms. So I'm going to have x times x squared. I have negative 2x, and negative 2x makes negative 4x. And then I have plus 4 and minus I squared, but what is I squared? Negative 1. So this is minus negative 1. So this is x times x squared minus 4x plus 5. And when I distribute that last x, I get x cubed minus 4x squared plus 5x, which was the original polynomial. So I want you to notice that the way we were finding the complex zeros was by the quadratic formula. And we came up with the plus or minus, means we had 2 plus or minus I. How are 2 plus I and 2 minus I related to each other? They're conjugates. So because the way you find the complex zeros is by the quadratic formula, they're always going to come in conjugate pairs. When you have a complex zero, its conjugate is also going to be a 0. So for example, x squared plus 4. I want to find its zeros, right? So I solve this thing. I get x squared equals negative 4. So x is the square root of negative 4 plus or minus, which is 2i. So I have two zeros, 0 plus 2i and 0 minus 2i. Conjugate pairs. So anytime you get a complex number as a 0, its conjugate is also going to be a 0. Complex zeros come in conjugate pairs. So those are the zeros, which means it would factor so then you put in its zeros, right? It's x minus one of the zeros times x minus the other 0. And the zeros are 2i and minus 2i. And instead of writing minus a negative, I'll put a plus. Okay, last thing. If a radicand, that's the fancy word for the thing under the square root, if it's negative, rewrite the radical in terms of I before performing any operations. So typically, when we're doing standard work with square roots, you're allowed to multiply the things under the square root, 20 times 5 and get 100, and the square root is 10, right? But when you're doing it with negatives, if I did that, I would get negative 20 times negative 5 is 100, and the square root would be 10. But instead of doing that, we're going to rewrite it with i's first. Okay, so this is like one of small difference between working with complex numbers and regular numbers. Square root of negative 20 is the square root of positive 20. What am I doing? The square root of positive 20 times I. And the square root of negative 5 is the square root of positive 5 times I. Square root of 20 times the square root of 5 is 10. We did that over here. And I times I is I squared. And what is I squared? Negative 1. So this comes out to negative 10. So basically, we have to make this small change because we don't want this problem, radical negative 20 times radical negative 5, to be the same as this problem. They should have a different answer because they're essentially different problems. Sure. I mean, rather than writing this all down, or yeah. Uh-huh. And then just throw a negative in front. Yeah, I mean, you'd get the right answer. Absolutely. And that would be a good shortcut for what we wrote down here. Yeah. Sure. Okay, so we have a little activity where I'm going to have you try to factor these polynomials. So remember, if you can get zeros, you got factors. So get the zeros, use them to write factors.